In this video, we're going to discuss the chain rule for the multiple variable functions, but we're going to start talking about the single variable functions in order to try to understand the similarities and the differences of the chain rule for the single and multiple variable functions. So if our function depends on an x implicitly through some function g, so basically we're given a composite function of the f and g, and if we still need to take the derivative of this function with respect to the x, so first of all we need to take the derivative of this function with respect to the g, right? So we are going to look to the g as a one variable and multiply this as the derivative of the g with respect to the x. For example, if we are given a function sine of x squared, and I need to find its derivative with respect to the x, right? So this is one function, our function f is a sine, g is the x, right? X squared, basically. So we're given a composite function. So if I would like to find its derivative, first of all, we need to find the derivative of the sine of x squared with respect to the x squared, right? What does it mean? It means that I need to look to this x squared, and x squared is one variable. My variable is called x squared, where x squared is not an operation anymore, right? It's the name of my variable. Multiplied to the derivative of the x squared, g, with respect to the x. So this is going to be the cosine of x squared multiplied to the tx. Okay, so I would like to obtain the similar formula to the multivariable functions. So now let's say we're given a function, the multivariable function z, as f of x and y, where x and y are the functions of the t. So let's do an example in order to obtain the chain rule. So let's say z is given as x squared y, where x is going to be cosine of t and y is going to be sine of t. So at the end, what I would like to do is, if I substitute the x and y to the z would depend only on t, and I just would like to understand what is the derivative of the z with respect to the t, right? And I would like to obtain the formula for this. But before doing this, I can do this manually by substituting x and y to this formula, to the z, right? If I would substitute the x and y to the z, I would get cosine square of t multiplied to the sine of t, right? And I can obviously take the derivative of the z with respect to the t easily by using the multiplication rule, right? So this is going to be derivative of this part multiplied to the sine of t plus derivative of the sine multiplied to the cosine square. So let us write this down. So it's going to be derivative of the cosine, it's going to be t cosine of t multiplied to the derivative of the cosine of t, which is minus sine of t, multiplied to the second function, which is sine of t, plus the cosine square of t multiplied to the sine, the derivative of the cosine, sine, it's the cosine of t. So let me rewrite this for a moment slightly differently. So let me write this as a t cosine of t sine of t multiplied to the minus sine of t plus cosine square of t multiplied to the cosine of t. So the reason why I rewrote this in this form is that I would like to obtain a formula for the z, right? So let me find the partial derivative of the z with respect to the x, right? So where I'm taking the partial derivative of the z with respect to the x, y is taken as a constant. It's going to be t x y, right? If I would substitute dx to be equal to the cosine and sine t here, it would be t cosine of t and sine of t, right? So where I take the partial derivative of the z with respect to the y, it's going to be simply x squared. If I would substitute this with the cosine, it would be cosine square of t, right? So now let me take the derivative of the x with respect to the t. So dx dt, it is going to be equal to minus sine of t, and dy dt is going to be equal to the cosine of t. Okay. Now, by looking out to this derivative, to this answer, I see these four components here. So I see that this term is actually equal to the partial derivative of the z with respect to the x. So this term here is actually derivative of the x with respect to the t. So this term here is the partial derivative of the z with respect to the y. And the last term here is the derivative of the y with respect to the t. So I will obtain this kind of formula. So the formula for the chain rule for the multivariable case would be dz dt is the partial derivative of the z with respect to the x multiplied to the derivative of the x with respect to the t plus partial derivative of the z with respect to the y multiplied to the derivative of the y with respect to the t. So this is called the chain rule of version 1 for the multiple variable functions. Let's do an example. So let's solve the exercise. So we are given a z to be equal to the x squared y plus 3xy in the power of 4, where x is going to be given as a sine of tt, and y is equal to the cosine of t. And we need to find the derivative of the z with respect to the t, and the t is equal to the 0. So in order to do this, we're going to use the chain rule for the multivariable functions. So the derivative of the z with respect to the t, it's going to be the partial derivative of the z with respect to the x multiplied to the dx dt, plus partial derivative of the z with respect to the y multiplied to the dy dt. So this is going to be equal to partial derivative of the z with respect to the x is txy plus 3y in the power of 4 multiplied to the derivative of the x with respect to the t is cosine of tt multiplied to the t, right? So plus, so partial derivative of the z with respect to the y, it's going to be x squared plus 12xy in the power of 3 multiplied to the derivative of the y with respect to the t, it's going to be minus sine of t. So I need to evaluate everything at the t is equal to the 0. So it's obvious that I can evaluate the cosine of tt and sine of tt by substituting t to be equal to the 0. But in order to evaluate x, y, and their powers, I need to evaluate them here. 0. So when t is equal to the 0, the x becomes sine of 0, which is 0. And when t is equal to the 0, y becomes cosine of 0, which is 1. Right? So I need to substitute all the appearances of the x was a 0 and all the appearances of the y was the 1. So it's going to be t multiplied to the 0 multiplied to the 1 plus 3 multiplied to the 1 in the power of 4 multiplied to the cosine of 0 multiplied to the t, right? Plus, so 0 in the square plus 12 multiplied to the 0 multiplied to the 1 in the power of 3 multiplied to the minus sine of 0, which is 0, right? So all of these terms are equal to the 0. And here, this term is equal to the 0. And what is left is 3 multiplied to the 2, which is going to be 6, right? So this term is also 0. So this term is 3, and this term is 2. So what is left is 6. So now we're going to look to another chain rule for the multivariable functions. So now, before, we used to have a function z which depends on x and y, which are another functions of the t only. And when we substitute the x and y to the z would be just a function of the t. Now, let's assume that the z depends on the t variables x and y, where x and y are also the functions of the multiple variables, right? So they are functions which depends on the two other variables, t and s. So when we substitute the x and y to the z is going to be a function which depends on now. So now when we substitute the x and y to the z, so z is going to be a function which depends on the t and s. So obviously I can find the derivative of the z with respect to the t as before, because now z's depend on the t variables. So what I can do is I can find the partial derivative of the z with respect to the t. And it appears it is going to be the partial derivative of the z with respect to the x multiplied to the partial derivative of the x with respect to the t, plus partial derivative of the z with respect to the y multiplied to the partial derivative of the y with respect to the t, right? Please note that I'm taking the derivative with respect to the t, so that is why here I have the derivatives of the t. So partial derivative of the z with respect to the s, that's going to be the partial derivative of the z with respect to the x multiplied to the derivative of the x with respect to the s, plus the derivative of the z with respect to the y multiplied to the derivative of the y with respect to the s. So let's do an example in order to try to understand how it works, right? So let's say we're given an example. So z is equal to the e in the power of x multiplied to the sine of y, where x is some function of the s and t, and y is also some function of the s of t. So what we need to do is we need to find, first of all, the derivative of the z with respect to the s. Let's say, so this is going to be derivative of the z with respect to the x, derivative of the x with respect to the x, plus derivative of the z with respect to the y multiplied to the derivative of the y with respect to the s. So derivative of the z with respect to the x is going to be e in the power of x multiplied to the constant, which is sine of y, right? So this is the derivative of the z with respect to the x. So I need to multiply this as the derivative of the x with respect to the s, right? So this is going to be, so s is a variable, t is a constant, right? So it's going to be constant multiplied to the derivative of the variable, which is t squared, right? Because derivative of the s is equal to the 1. Plus, I need to take the derivative of this function with respect to the y. So that is why I will look to this as a constant. And this is going to be a constant multiplied to the derivative of this function, which is cosine of y, multiplied to the derivative of the y with respect to the s. It's going to be ts, right? Multiplied to the constant t. So analogously, I can find the derivative of the z with respect to the t. This is going to be this formula. Now, again, so the derivative of the z with respect to the x is e in the power of x sine of y, multiplied to the derivative of the x with respect to the t now, right? So I will look to the s as a constant. It is going to be tt multiplied to the constant s, plus derivative of the z with respect to the y is e in the power of x multiplied to the cosine of y, multiplied to the derivative of the y with respect to the t. It's going to be some constant multiplied to the t. It means just simply constant, right? So this is how the chain rule of version 2 works for the multivariable functions.